Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about Taylor and Maclaurin series. So for some reason, I remember when I was taking Calculus 2 in university, people found this section the hardest, but I personally found it the easiest out of everything just because it was such a simple procedure. You just simply had to do it a couple of times and then just make a little observation. So I'm going to try to dumb this down as best as I can for you guys, but essentially the whole lesson is based off of this kind of concept, and it's that if we have a power representation at A, so meaning we have some sort of function equal to this series right here, this power series. Obviously we do give the radius right here of convergence, but then what we say is that the coefficients are given by this formula right here. And obviously there is going to be a formal proof to it. I'm sure you can find it somewhere on the internet, but it's going to be a little out of the scope for this. So just know that the coefficients for this power series representations can be written as this. And it's basically just the nth derivative of that function at A, whatever the center is right here. And then we just want to divide by the n factorial. And I'm going to show you basically how to do that, but as you can tell, this lesson is titled Taylor and Maclaurin Series, and there's a simple differentiation between the two. So a Taylor series is basically going to be centered at some sort of value which we'll call A. However, a Maclaurin series is just going to be centered at 0. And that's just basically the key distinction. Maclaurin series is kind of a subset of Taylor series. It's just the special case when A is equal to 0. Now, I'm going to show the entire procedure for finding a power series representation using Taylor series through an example. So I'm not going to go through a couple formal steps because it's fairly simple. All we have to do is literally apply this formula right here a number of times and then kind of see a pattern from it. So I'm going to go ahead with two examples, one for Taylor series, one for Maclaurin series, and then hopefully from there you can kind of get the hang of things. So let's say we are given this example and we're asked to find the Maclaurin series of a function f of x is equal to e of x, or e to the x. So in this case, what we know is that this is a Maclaurin series, so that means a will equal to 0. As I mentioned, the only thing that we're going to be doing really is just applying this formula right here. So we basically want to take the nth derivative centered at a, and then we would want to divide by n factorial. And I'm just going to show you how we can go ahead and apply these sort of calculations for these coefficients. So let's start off with c at 0. Well, c at 0, that means n is 0. So we're going to take the 0th derivative at a, and a in this case is 0 because, well, we've labeled it here and it's a Maclaurin series. And then we want to divide by n factorial, but n in this case is 0, so it'll be divided by 0 factorial. If we're going to simplify this, well, the 0th derivative, what that means, it's not the derivative, so it's just the function itself. So it's basically e of x at 0. So I'm just going to write e at 0 divided by 0 factorial. And well, e to the power of 0, well, that just equals to 1 over 0 factorial. And obviously you can go on to simplify 0 factorial to equal 1, but I'm not going to go ahead and do that. I'm going to show you later on as to why I won't be doing that just for this example, but by all means you could. So now on to c1, we're going to compute the first derivative still at 0, and then we want to divide by 1 factorial because, well, n in this case is going to be 1. So, well, the first derivative of e to the x, right? Well, the derivative of e to the x is just e to the x. And then it's saying compute the first derivative at 0, meaning it's just f prime at 0, but f prime is equal to e of x, so it's just e to the power of 0 again. So this is e to the power of 0, and then we want to divide by 1 factorial. E to the 0 is 1, and then I'm going to leave it as 1 factorial. Now for c2, well, we're going to take the second derivative at 0 and divide by 2 factorial. And the second derivative of e of x, well, it's just e to the x, and then we want to plug in 0, so we're going to get e to the 0 again over 2 factorial, and this is simply going to equal to 1 over 2 factorial. Now you can kind of start seeing the pattern, but I'm going to go ahead and just do C3 over here. So we're going to compute the third derivative of this function at 0 and divide it by 3 factorial. Again, the third derivative of e to the x is just e to the x, so it'll be e to the 0. And then we want to divide by 3 factorial, and this is going to be 1 over 3 factorial. Now if we combine everything that we've got in all of these results, well, let's kind of write out the terms that we have. So we have 1 over 0 factorial, and then obviously this is going to be x to the power of 0. I'm going to leave this here, but it is there. Just note that it is there, even though it's not often written. So then the next term for C1, well, that's going to be 1 over 1 factorial. I'm basically plugging this term in now, and it was equal to this value. So that's the coefficient. And then we're going to have x to the power of 1. Why? Obviously, it's because we are keeping this chunk right here. So it's x minus a in this case is 0 because it's a Maclaurin series. And then we are going to have n. Well, in that case, we were doing C1, so n was 1. That's why we have x to the 1. So now for C2, this means that n is 2. This right here is going to be the coefficient. So we're going to have 1 over 2 factorial. And then it's going to be x to the power of 2 because n is 2. And lastly, for C3, well, the coefficient is 1 over 3 factorial. And then x is simply going to be cubed in this case. And then we're going to keep going. So as you can see, there's a pretty obvious pattern. The denominators right here are simply the factorials of n. So again, these power series, or these Maclaurin and Taylor series, they all start from n is equal to 0. So in this case, all that's in the denominator is just n factorial. And then in the numerator, well, we can always see a 1 right here. So it's, I'm not even going to write it, but you can put a 1. And then what else do we see in the numerator? Well, we see x to the power of 0, 1, 2, 3, and that is obviously going to be x to the power of n. So if we want to simplify this and basically just get rid of that 1, it's going to be the same thing, but without the 1. It'll be x to the n over n factorial. And there is our Maclaurin series for this function. Again, it's nothing really difficult. We just keep on applying this formula right here until we start slowly seeing a pattern from it, and then we kind of write it in this sigma notation. So for this example, I've chosen to use the same function right here, which is f of x is equal to e to the x, just so we can see how the two differ. And in this problem, we are asked to find the Taylor series at a equals 2. So that's given to us. So now let's start the same process. Let's start off by computing maybe 3 or 4 terms just to kind of see how the function looks like, and then we can slowly write it in sigma notation. Just to remind you, the formula for the coefficients Cn, well, that's equal to the nth derivative at a, and then we want to divide this by n factorial. So for C0, meaning n is 0 in this case, we want to compute the 0th derivative at a, in this case a is 2, and then we want to divide by 0 factorial. The 0th derivative is just the function, but we want to compute it at the value x equals 2. So it'll just be e squared over 0 factorial. Now on to the next coefficient for C1. Now we want to compute the first derivative at 2 and divide by 1 factorial. Well, the first derivative of e to the x is just going to be e to the x, but we want to compute it this time at x equals 2. So it'll be e squared, and then we want to divide by 1 factorial. C2 is now going to be the second derivative at x equals 2 of e to the x, and then we want to divide by 2 factorial. Well, this, again, the second derivative of e to the x is just equal to e to the x, so it'll be e squared in this case. And then we want to divide by 2 factorial. And you can almost guess what the third derivative will be. This should be 3 factorial. So again, it's going to be e squared over 3 factorial. So now if we write these terms all together, we are going to get that e squared over 0 factorial. And then we want to do x minus a. In this case, a is 2, so we want to write x minus a, which is 2, so x minus 2. And then we want to write the to the power of n, so it'll be to the power of 0. Then we want to add on the c1. So c1 is e squared over 1 factorial. That's the coefficient. And then we want to do x minus 2 to the power of 1. Then we want to write the second coefficient, so c2. In this case, it'll be e squared over 2 factorial, and then it'll be x minus 2 squared. and then I'm actually going to write the last term over here. So for C3, it'll be e squared over 3 factorial, and then times x minus 2 cubed. Again, these values are coming from here, right here, this chunk of that series. So Cn is generated by this formula right here, and then the rest of the kind of term is generated by just plugging in the n value into here and subtracting x minus a and then raising it to that power. That's it. So now that we have this written out, well, we can start forming the sigma notation for it. What do we see on the top? Well, in the numerator, we see that we have a constant e squared. So we're going to keep that there. In the denominator, once again, we can notice that it's 0, 1, 2, 3, meaning that it's incrementing. So it'll be n, and then we want to take the factorial of it because, well, it's 0 factorial, 1 factorial, 2 factorial, and then 3 factorial. And then, actually, I'm going to make this a little bit smaller. So after that, these are the coefficients, but then we see this x minus 2 right here, and it's raised to the power of first 0, then 1, then a 2, and then a 3, meaning it's variable, so it's n. And then this is now the Taylor series for this function centered at a equals 2. So again, the steps are fairly simple. Just find these coefficients, write them out as a function, and then from that function, turn it into this series notation, or like sigma notation, whatever you want to call it. For this last part of the video, I'm not going to go ahead and find all of these Maclaurin series for you, but basically the process is always the same. Just find the coefficients, write the function, and then from the function you can kind of figure out what this series notation will look like. But here is a table of important Maclaurin series. You can kind of memorize them or like know them, and then from there it will kind of help you. I've also written down their radiuses or radii of convergence, so that might help. And again, you might want to kind of remember this table. It can probably help you on like a test or exam or something. So yeah, that's it for today's video on Taylor and Maclaurin series. Again, I think it's a pretty straightforward concept. Just find the coefficients, put x minus a to the power of whatever the n is, and then from that function notation you can slowly go into the series notation. So I think it's pretty intuitive, pretty straightforward. Hopefully you guys enjoyed this video. If it's helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.